Okay, let's go and get started today. This is going to be a relatively short lecture as we're not really going to cover any new material. We're just going to talk about what you need to do for that lab assignment for Lab 5. And essentially what we're doing for Lab 5 is we're going to communicate with a chip that uses SPI as its communication interface. And specifically, we're going to talk to a chip that's called an NRF24L01 plus. And what that chip is that chip is a wireless transceiver chip that can both send wireless data, receive wireless data. So let's go and take a look at what we're going to do here. Now, for this lab, we're going to write a program that talks over SPI to that wireless chip. You're not going to be getting the chips to communicate with each other for this lab. In other words, you're not going to be using any of the wireless capability. We just want to make sure, can I read registers from that chip? And then ultimately, can I write registers to that chip? We're not going to do any writing to it today, but it's the same process that you'd use to write over SPI as read over SPI. So the idea here is we want to read the chip's registers over SPI. And you're going to do that through the Arduino. So you're going to use the Arduino to send, be the SPI master. It's going to pull the select line low, manipulate the clock signal. It's going to shift out its shift register, shift in the other register, and then you're going to read that response from that. So let's take a quick look at reviewing the SPI interface before we look at the lab assignment. So the way SPI works, as a reminder, you have a slave device. In this case, this is going to be that wireless chip. And we have a clock, SDI, or MOSI, MISO, and slave select. So what we're going to do in the Arduino is we're going to pull the slave select low, and then we're going to write an SPI function that does all of the stuff that we want to do here. In other words, the SPI function that we're going to call is going to shift a bit out, tick the clock, put the next bit out, tick the clock, put the next bit out, tick the clock. But every time it ticks the clock also, it's going to shift a bit in. So it's going to have 8 bits that go out, 8 bits that come in with the same clock signal. And then after that, that SPI function is going to return that 8-bit byte that it got. So in other words, we're going to make an SPI function that we pass a byte to. It ticks the clock 8 times, shifting a bit out and a bit in each time. And when it's done with all 8 bits, it's going to return to us whatever came back as a byte. So this is typically how SPI implementations work. We're going to do a software SPI implementation for this, but we're going to then look at the data sheet for that chip, and we're going to figure out how to read the registers of it. All right, so multiple slave devices might be connected to that single master, but in our case, we're only going to have one connected. We're just going to have the one, so only one slave select. But if you wanted to connect other SPI devices, you could share these 3 lines. We would just need an additional slave select for any other device we add. Okay, and as a quick review of what happens every time the clock ticks, we want to have the most significant bit go out onto MOSI, and then whatever came in on MISO is going to come in. So we're going to have just 2 I/O lines for this. So that'll be laid out in the lab sheet what I/O line you should use for which bit. But essentially, you're going to say mask a bit, the most significant bit from this byte, put it out on the output, the MOSI output, and then shift in. We tick the clock, shift in whatever was on MISO into the least significant bit of some other byte, and then shift everything over by 1, and then repeat it at 8 times inside of a for loop. And once we're done with that, we will have the ability to talk to that device, and we'll look at the data sheet for how to do that. Okay, now these are the transaction sequences from a different device as a review from last time. But the idea here is, again, pull the select line low, tick the clock, 8 bits go out. If we tick the clock, another 8 bits come in. We're going to look at that in the actual data sheet for the chip we're working on here in just a second, so just bear with me. Okay, for this lab, we're going to be using these modules, and really these modules only have that one chip on them and then the supporting hardware for that chip. So there's some capacitors and things like that, and a crystal that goes to this chip. But they're really simple. They're also very low cost. These cost about $1.28 a piece, $1.29 a piece, which is remarkable. And there's actually kind of a reason for that we'll talk about, that these are probably using knockoff chips rather than ones directly from the manufacturer. But they're really widely available. Some of them have real chips, some of them have knockoffs that are almost identical, but these are really a popular chip that it's used in a lot of things, from toys to like the Xbox 360 wireless controllers use a version of a chip that's very similar to this. That's kind of what this was designed for, was kind of that wireless remote control kind of interface applications is what that chip was designed for. Well, somebody made it convenient and made a nice module out of it that includes this like PCB antenna on it. So you don't have to connect an antenna. You just plug in the right signals into this module. And you're going to use those DuPont cables, style cables, little cables. You can plug a female end into this and a male end into the Arduino. And this just has these 8 pins. For this lab, we only really need to connect 7 of them. And we'll talk about that in a second. But for this lab, you only need 1 of these because we're just going to be talking and making sure we can communicate with it, read its registers back out of that chip using SPI. Next lab, we're going to get these things to talk to each other wirelessly, and this one to send a message, that one to receive the message between the 2 Arduinos. So kind of like what we did in the previous labs, but with no wires, which is actually pretty cool. And let's take a closer look at these modules for a second. So if you look at these modules, here's kind of the output or the layout of it. And here's the header. This is a top view. So looking at the top view, here's what the pins are. So this one in this corner right here, the kind of lower right corner is ground. And then next to that is VCC, which is power, which is going to be 3.3 volts in your application. And then you'll notice we have 2 enable lines. We have CSN, which is the chip select not. That's where our slave select is going to go. But we also have CE. And what CE is a chip enable. That really enables the radio power to the radio module on this thing. So in other words, you can have the radio part powered down, but still talk to the chip and configure it and then power this up once you're ready to communicate. And the reason they have a separate enable for that is a way to save power. The biggest source of power draw from this is having the receiver parts of this chip on and listening to that line and amplifying things. So they have a way, this chip itself has a way to turn on and off just the radio part, or select it to talk to it and communicate with it. So in our case, we're not going to have to worry too much about that right now. But then notice we have SCK, that's the SPI clock, MOSI, that's SPI, MISO, that's SPI. And then there's an interrupt request that you could configure that when it receives a packet, it sends you an interrupt to tell you. In other words, when a packet comes in, that interrupt line changes state to say, hey, somebody talked to us, come and get the packet. We're not going to worry about that right now. But again, here's what those look like. You can see that PCB trace antenna that's on there. It's kind of squiggles back and forth to get it to be exactly the right length needed for a 2.4 gigahertz spectrum. It also has this, what they call an inverted F design, which really just looks like an F. But you'll notice that this part here adds what's called counterpoise for this part over here. But there's a certain geometry for designing these PCB trace antennas like this that is designed based on the frequency and the length of the antenna and the surface area. And that's getting into something that's more complicated than what we want to do in this class. But notice we're just going to be talking to this chip. And you'll notice if you look on this board here very closely, you can see those are just straight shots to the chip. The chip itself basically just has an SPI interface. This stuff up here is all capacitors for kind of the RF stuff for communicating with this chip. But for the most part, we're just talking directly to that chip and telling it we want to read its registers. So let's dig into that a little bit further. And let's start out with looking at the data sheet for the chip. And this is well, should be a link directly to the company that makes the chip's website, but I already have it up in another window, so let me just switch to that window and you can look at it. In your case, you can go ahead and click on that, pull it up and look along with me if you want to, or you can just watch what I'm doing because I'm going to kind of take a look at that data sheet. Now, since all we care about for this lab is looking at reading registers, that's what we're going to focus on right now. We're not going to look at the whole data sheet and read through the whole thing. We're just going to take kind of a quick look at that. So here's the data sheet. And you notice this is a company called Nordic Semiconductor. And this is the NRF24L01 plus. Sometimes that'll end with a P. NRF24L01p because plus is a hard thing to put in there, but the actual part number is that thing that's listed there. And you'll notice it says it's a single chip 2.4 gigahertz transceiver. And what a transceiver is that something that both can transmit and receive all in one unit. So in other words, if we think about what we've been talking about in the wireless class, we have a channel and things can put things onto the channel, and then that's a transmitter, and the receiver pulls things off the channel. But in this case, we have a device that can both put things onto the channel and pull things off the channel. So it can both talk and it can listen. And that's what a transceiver is. Now, if we look at this, you'll notice that it's a really small part. It's 4 millimeters by 4 millimeters. It's got 20 pins in the package. And you'll notice it has on-air compatible in 256 kilobits per second. So that's pretty fast. That's faster than what we were able to do with our wired connections, or we did with our wired connections. And it can go all the way up to 1 megabit per second here, or it can actually do 2 megas per second. So it can be 250,000, a million bits per second, or 2 million bits per second. So this is actually a pretty quick chip, and that's it also is fairly low latency, which is why it was designed for things like wireless game controllers or things like that, with those things in mind. Now, the other thing you'll notice about this, looking at the data sheet here, is there's some stuff that we're not going to worry too much about, but it's a fairly low power, so it doesn't take a lot of battery power, which makes it great for battery-powered mice or things like that. It's actually a pretty cool chip. It's a useful chip to learn. It's very widely available, like I said earlier, and it's fairly inexpensive. The details of how we're going to talk to it, let's take a look now. I'm going to skip over some stuff here. You can skip over this as well. But notice there is a table of contents. Let me shrink this down a little bit so we can fit a little more on the screen at once. But you'll notice it's got the pin information or the pin assignment. It's got this block diagram. And if you scroll down through here, the part that we really care about is going to be how do we talk to it. But before we do that, I want to quickly look at some of the other parts of this data sheet. So let me just jump to the introduction here. And one of if you read through this kind of describes some stuff about the features of it. You'll notice it's in a 2.4 gigahertz spectrum range. It does support a number of different channels within that range, so you can select what channel you want within that range. And you also might note by reading through this that it does say the register map is accessible through SPI, and it contains all the configuration registers and is accessible in all modes of operation. So that's what we're interested in. In other words, the way you talk to this chip to get data into it, or to pull data out of it, or to configure it, is all through this SPI interface, which makes it really convenient. So if we can talk to this thing over SPI, then we can read a register to get data out of it, can write a register to put data into it, and eventually what we're going to do is we're going to write packets into it, read packets out of it, read the status register to know when we should read a packet or when we should write a packet, and so forth. But this is actually, if we can talk SPI to this from our microcontroller, we could set this thing up to transmit or receive. And that's what we're going to focus on today. Now, moving on for a second, here's some stuff that's, I guess, features of the thing. Now, one of the things that I'm going to look at just for a second here is you'll notice it has 126 RF channels that we can choose from. So it's kind of like channels on your TV. You can pick one of 126 of those. You'll also notice it talks about modulation, this GFSK modulation. We're not going to talk about modulation right now and how wireless works because we want to focus just on the SPI part. But later on, we might talk a little more about different modulation techniques and how those work. But for right now, all we care about is SPI and being able to talk to this. We don't care about the wireless stuff right now. But when we get around to that, notice you can have up to a 32-byte payload for each packet. And it also has the ability to kind of automatically sort those packets into one of 6 pipes that as packets come in. It also has a buffer built in, like a little FIFO buffer that basically has 3 buffers worth of 32-byte packets each for both transmit and receive. So as a packet comes in, another one comes in, they can kind of build up in that buffer, and then you can read them out when you check the status register to notice a packet has come in. Now, notice down here, what interests us, 4-pin hardware SPI interface. That's what we're interested in talking to this thing over. So let's scroll down. There's like a block diagram as a transmitter section or receiver section. Those connect out to that antenna. There's like a crystal input that comes in, and then over here's this SPI where we talk to that over SPI. When we talk over SPI, we have access to the registers internally. We have registers to the receive FIFOs that have the data that came in, the transmit FIFOs that have the data that's going to go out. And then there's some control registers over here that have configure things about what channel and what power level and things like that. So pretty cool chip that we can access completely through SPI. And there's what the chip looks like, 4 millimeters squared, and there you can see the pins. The antenna connects here. But you'll notice it's got power and ground, it's got the crystal that connects to there. But the thing you might notice is over here, there's the slave select, the CSN pin. There's the clock, the SPI clock, MOSI, MISO. You connect those 4 pins, we can talk to that. But again, it does have this CE that enables the radio, and it's got this IRQ that can tell us when a packet shows up if we use it as such. And the rest of it, this stuff is we don't have to worry about on our module. They've already taken care of the capacitors and the voltages and the crystal and the everything needed to connect to the antenna. So all we need to do is focus on those connections that come out of that module. Okay, so moving on a little bit farther here, let's actually go to how you talk to this thing. So somewhere in here is information about the SPI interface. And if you've never looked at a datasheet before, this is more complicated than the ones we looked at previously, just because it's a more complicated chip. Notice that it has different modes internally that goes to like this low power standby mode, and then you can go here to transmit stuff, transmit mode. Once it's done sending a packet, it'll go back to standby automatically. Or while you're here, if it gets, if you do that chip enable equals 0, you pull it, put the chip enable into this, pull it low, it goes into this, or put it high, it goes into the RX settling mode, which goes to receive mode. It receives that packet and when one comes in, and then it goes back to standby mode again. You can also put this thing into a low power mode by setting this power up register bit into a low power mode where it automatically goes and conserves power through the programming interface and so forth. But you'll notice that this is something that later on we might look at to figure out how to use this thing. We don't have to worry about that right now. All we have to worry about is the SPI stuff. So let's go ahead and look at that part. So I'm going to scroll down here. There's what the packet looks like. There's the up to 32 bytes worth of payload. And you'll notice it has this preamble byte, an address that's 3 to 5 bytes long, and then this packet control field, and then it has a CRC at the end. We haven't talked about those yet, but that's a checksum, check value that makes sure that this hasn't been corrupted when it was transmitted. We'll talk about that later. Okay, so now we should be coming up on where the SPI stuff is. Okay, so here we are with the data and control interface. And this is a section you probably want to look at. So this is, notice page 50 of this document. But you'll notice it says, the data and control interface gives you access to all the features in the NRF24L01p. The data and control interface consists of the following 6 5-volt tolerant signals. So that's important to note. This is a 3.3 volt chip, but the input pins are 5-volt tolerant. If you want to connect other things to your Arduino, just be careful that some chips are 3.3 volts, and if you put them at 5 volts, it'll damage the chip. But this is these are 5-volt tolerant digital signals. That's good for us because we're going to power this thing at 3.3 volts, but we're going to talk to it at 5 volts. And this says, part of the datasheet says, that's okay to do. So in other words, this is like some chips, if you put more voltage in than they're expecting voltage, for those of you who don't know, it's kind of like a electrical pressure. It's how much pressure there is. So the higher the voltage, the higher the pressure, which is why high voltage lines high voltage that builds up on your hand when you rub your feet on the carpet makes a spark, or the lightning is incredibly high voltage that then discharges. So in some chips might be damaged by putting more pressure on those pins, more voltage than they're designed for, this one says they were designed to be tolerant of 5 volt digital signals. It's good for us. We can use them with the 5 volt Arduino that we have right now. Okay, so here's the signals. IRQ, that signal's active low, controlled by 3 maskable interrupt sources. We're not going to worry about that now. CE, the signal's active high. It's used to activate the chip in RX or TX modes. In other words, CE is the thing I talked about that activates the radio. CSN is an SPI signal. That's the slave select, SCK, SPI, MOSI, SPI, MISO, SPI. And you'll notice down here it says that the SPI interface can go up to 10 megabits per second. So we can talk to this thing pretty quickly. 10 million bits per second over SPI. Has an 8-bit command set. It's easily configurable through the register map. And it has full 3-level FIFO for both TX and RX. All right. So here's the SPI operation. And it says, the SPI commands are shown in table 20. Every new command must be started by a high to low transition on CSN, which is the slave select line. Just like every other SPI device, every command is started by pulling the slave select low. And then it says the status register is shifted out on the MISO pin simultaneously to the SPI command word shift, or shifting to the MOSI pin. So that means that whenever we shift out a command, it automatically tells us the status. So this is a case where this chip is truly using that full duplex nature of SPI. And then you'll notice essentially it sends out a command word, and then there are data bytes that follow that. So let's actually look at the pictures for this, but let's look at the register set first. So notice here are the registers, or the commands. That's the first thing that gets shifted out. And the first one here is this read register command. And this is in binary here. And this is the only one we care about for this lab. Notice for the next lab where we actually want to talk and write data to the payload register, or read data from the payload register, or do any of these other things down here. But all we care about is reading registers up here. So we're going to use this command. So notice the thing that distinguishes this command from the other is it starts with the bits 0, 0, 0, and then we have the address of the register, that 5-bit register in the address map that we want to read. So if I wanted to read register 0, I'd pull the chip select low, and I would shift out 0, 0, 0. It says I'm going to read from a register, and I have 0, 0, 0, 0, 0 in those next 5 positions there. So that says read from register 0. And then the next bytes that I shift would then read the next 8 bits that I shift, or the next SPI transaction would read in whatever the contents of register 0 was. And then when we were done with that, we'd set the chip select line back high, the slave select back high, and now we're back to waiting for the next command to be shifted out. So pretty straightforward. But so notice all we care about is this command here. And again, this is on page 51 of the data sheet. All we care about is this read register. Notice to write register, it's the same thing, but we put a 001 followed by the address. Now let's take a look at, here's a chart of how the SPI read operation works. So again, chip select goes low. There's the clock pulses that we're going to send out. That's going to shift out the command that we want, which in our case is going to be 0, 0, 0, followed by the address that we want. And then the next clock pulses are going to be it shifting data back that matches whatever register we asked for. Now, most of the time, most of those registers are only 8 bits. So it'll only be in this period here. And then we'll set the chip select by high. But some of those registers have more than 8 bits. And we're going to talk about that here in a second as well. And SPI write, which you don't have to worry about right now, works the same way. We just put the command word for a write in here. And then we shift out, put out the data that we want here during those clock periods. All right, so let's go down and look at the details of how those commands work. And this starts on page 57. And notice the way that this is set up. This is saying register 0 is the config register. And register 0 being the config register, these are what all the different individual bits mean in that register. Now we don't really care about that right now. We just want to have it output what the contents, the value of that register is. So in this case, register 0 has 8 bits, 0 through 7. But here's what the meaning of it is. So later on when we go to configure this thing, we're going to have to figure out how to set this thing up by, for example, putting it in power up mode, by putting a 1 in this particular location, in bit 1. And then we either set it to be in transmit mode or in receive mode. Most of the time we'd be in receive mode, but then we want to say something, we would switch to transmit mode, send that packet, and then once that packet's done, switch back to receive mode. And then there's some other stuff here that we're not going to worry about right now, but all you're going to do is you're going to read out those things. Now, how can you tell if your program is working correctly? Well, there's an easy way to do that. Notice it shows what the reset value is of this chip when this chip first powers up in here. This is the bit pattern that you should see. So in other words, what we should see in register 0, if I read that out, would be 0, 0, 0, 0, 1, 0, 0, 0. So that's 1, 2, 4. That's 8's place, or in hex, you should see 0x08 as what you read on reset. And the next register, register 1, you should see 0011, 111. That would be 0x3f in hex, or 63 in decimal. And then for register 2, all of these read out as zeros except those. You should see a 3, 0x03, or just a 3. And then you should see a 3 in this register, a 3 in that register, and so forth. Now, where this gets a little bit confusing on these registers is when we get down to here, also 0 through 9, all those registers are just 8 bits. But when we get to register 0A, you're going to have to make a different function for handling printing out that one, because that one is 40 bits long, and that is the receive address, which by default is E7, 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 E7. So that one you're going to have to pull the line low, clock out that you want to read register 0A, but then you're going to have a for loop that goes through for each of these 1, 2, 3, 4, 5 bytes. So you're going to have SPI get the first byte, SPI get the second byte, SPI get the third byte, SPI get the fourth byte. So 0, 1, 2, 3, 4 for each of those, and then print out each of those as you get them. Also notice that you're going to, for 0B, 0B is also an 8-bit or a 40-bit address, not 8. But then it returns to 0C, 0D, 0E, 0F. Those are 8 bits. But then register 10 hex is a 40-bit. So you're going to have kind of 2 versions of the read register function. You're going to have one that's an 8-bit version that prints out whatever it gets back, and one that's this 40-bit version that takes 5 bytes and prints out whatever it gets back. And then it goes back from there on. It's just printing out. The rest of those are 8 bits from that point on. Now, there are these other things that we can read that are these kind of transmit payload, receive payload, and acknowledge payload, but those are accessed through a different command, which is why it says the hex address is not applicable, and it actually tells us in the description, written by separate SPI command. But essentially this ends at register 17, and then there's 1C. So you're just going to have to write a loop that goes through and reads, write code that goes through and reads each of those registers. I guess there's also a 1D, and that's it. So you're just going to print out all those. Now, let's now that we've looked at that, let's review kind of how you're going to write this in code. If you remember from last time, we talked about kind of a software SPI function implementation, and where on the Arduino you're going to basically tick the clock, shift a bit in, shift a bit out, and so forth throughout the entire thing. And we looked at that last class. So if you're fuzzy on that, I would go back and look at that. But let's go and take a look at go back to the presentation for a second and then look at the lab sheet, because I think that will be helpful to you. So give me 1 second to switch back. Oh, let's look at the lab assignment sheet. So I meant to switch to that. Hold on, give me 1 second here. Almost there. And this is lab 5. So there's lab 5. So here's what the module looks like, and to make it easier for you, I've labeled the pins, and then I've given you a map for what you should connect to where. So in other words, ground will connect to ground. VCC, this pin here, remember this is a top view, so you're going to be connecting to the bottom of that, so don't flip it over and have them all mirrored. But VCC, you're going to connect to the 3.3 volt pin on the Arduino. CE can connect to pin 7, although we're not really going to use that right now. You could leave that one disconnected for this lab because CE doesn't really matter, because we're not going to be turning the radio on and using it. CSN goes to pin 8, SCK to pin 13, or GPIO 13, MOSI 11, MISO 12. And the IRQ, just don't connect that one. You don't need that one right now. And realistically, you could get by with not connecting this one too. The reason I have it going ahead and shown here, because this is how we're going to connect it for the next lab also, where we get these things to talk to one another. And one thing that might help is for you to write out the colors of what goes where for the wires you're using. That can make it more convenient. Okay, then now the next thing that you're going to do is you're going to write this software SPI function. And that software SPI function, I've given you kind of the comments for the pseudocode for that. But in other words, you're going to pass in an unsigned character. That's just an 8-bit byte. And it's going to do its processing, and it's going to return an unsigned character, which is an 8-bit byte. So we pass it in an 8-bit message. It returns to us an 8-bit message. And that's essentially how SPI always works. You say shift out this 8 bits, get this 8 bits shifted back into us. So here's the pseudocode for how you're going to do that. You're going to make this unsigned character for a receive byte. That's what's going to get returned. But then you'll notice I have the pseudocode here. It says loop through 8 bits. In other words, you'll just have a for loop that goes through 8 times for each of the 8 bits. Write the SPI MOSI line either high or low, depending on the bit value that we're sending out. Now that's going to be the most significant bit value. How do you get the most significant bit value? Well, you want to OR with 0x08, just like you did in the previous lab. And if that turns out to have a 1 in that position, or turns out to not be 0, then you set that line high. In other words, you set the MOSI line high. If it's a 0 in that position, if that and 0x80 is 0, put a 0 out on the MOSI line, which in this case is GPIO 11. And what I would do if I were you is in my code, what I did is I made pound defines. I did a pound define MOSI as 11, pound define MISO as 12, and that way in my code, the way you write the code, is you can say digital output MOSI high, digital output MOSI low, and so forth. So it makes the code a little more readable. And if you ever wire this differently at a different time, you just change the pound defines and you don't have to hunt down everything in the code. Now, delay for 1 unit of SPI clock time. And what I would suggest doing is running this relatively slowly at first and then speeding it up later. So maybe, I don't know, put 10 milliseconds there or something like that initially. But later on, you can actually speed this thing up quite a bit, because remember, the chip will go up to 10 megabits per second, which is a really slow, small clock time there. So then we we delay. So this is the ticking of the clock. We set the line, put the line out there. We did a delay. We then set the clock line high. After we set that high, we read the MISO line to see what it shifted back to us. and we add it to this receive byte by ORing it. You're going to put that on the least significant end. Delay for 1 unit, set the clock line back high, and then you're going to shift at the top of the loop, you're going to shift that over. At the bottom of the loop, you're going to shift the other one over. And I want you to kind of figure out how you do that, but this is very similar to what we did in that synchronous lab previously. So see if you can figure out how to write that software SPI yourself, and I kind of gave you the pseudocode for it here in the form of comments. But then after we're done with this, going through this loop 8 times, in receive byte, since we ORed all those together and shifted them all over, we'll have whatever the module sent back to us. And then we're going to return that. Okay, so a couple things here. In the setup, you're going to do this. You're basically going to set up all of those lines. MISO is an input, clock is an output, C is an output, CSN is an output, MOSI is an output. And I don't know why clock is on here twice. That should only be on there once, but whatever. And then what you're going to do is read a key from the serial interface of the PC. If they press an R or a capital R, then you're going to just display all the contents of the registers on a screen, kind of in a table format. And I want you to display those registers in hex and in binary. So if you're confused on how to get this to print in hex and binary, you can either Google that or if you remember, we did a lab last semester in systems programming. They read things in hex and binary, or printed things in hex and binary. You might look at that from systems programming class. But keep in mind that you can, there's some, since there are some additional features for the Arduino, you could just say how to print in binary Arduino, and it would show you how to do that. How to print in hex in Arduino. And there'll be some code that shows you how to do that. All right, now as far as hints, remember that the CSN line is the equivalent of the slave select. So we're going to have to pull that low, then clock things out. And I actually describe that down here. So it says to read a register, pull the CSN line low, then call the SPI command for read register that has the correct address in it. So since the upper bits are just 0, it's just going to be the address value. So you're just going to shift out the address value you want to read from. And then you're going to read the contents using an additional SPI call. And then capture the return value. And then when you're done, you set the CSN line back high. And what I would suggest doing is writing a read register function that encapsulates all that. Pulls the line low, shifts the register address out, whatever comes back in over, or calls it again, whatever comes back in over SPI, returns that. And then I would make another function called a read long register or something like that works for the 40 byte ones. And that's kind of this last note. It says note most registers are single byte value in size, or single byte in size, but some are 5 bytes. To read these large registers, call the SPI command multiple times while leaving SPI or the CSN line low. So pull the line low, send out the command, and then 5 SPI calls, soft SPI, soft SPI, soft SPI, soft SPI, soft SPI. Capture each of the return values, maybe stick them in an array or something like that, and then print out the contents of that array. So run your program, verify you're reading the correct register values from the module by looking at what the default value should be. And then what I want you to do is capture the output of that program and submit that as a text file along with the source code. And that's it. So this was going to guarantee, or by running this, if you see those values in there and you see different values in the different registers and they match what the datasheet says the reset value should be, you know you're talking to that chip. And that's going to make it much easier for the next lab when you actually get the chips to communicate, because we can read from that register, the registers of this, then we can write to them. And if we can do those two things, then we can actually configure these to communicate with each other. But first step, wire it up. Second step, write the software SPI function. And what I would do is focus on getting it to read just one register first. If you can read from that first register in there and get the value that it's supposed to be, maybe the first 2 registers, If you can get those values coming back, then you have the building blocks to do the rest of it. But the key is going to be making sure your software SPI function is written correctly. Try to follow what's going on here. And I've obviously left out some of the details, but if you look at that synchronous lab we did, or pseudocode from last time, or your code from lab 4, that's going to be a big help at getting this to work. And now maybe you see why in the systems programming class I spent some time on bitwise operators and shifting and things like that, and you can see how useful they are here. Okay, so let's go back to the presentation just for a second. So that's all I'm going to cover today. I wanted to leave you plenty of time to work on the lab and get started on that. And so get started on that. And next class, we're not going to work on the next lab just yet. I'm going to spend a little bit of time talking about another topic called self-clocking codes. And I might give you more time to work on this lab because getting this one to work is going to be critical for getting the next one to work. So I want to make sure everybody has this working. Really, the amount of code you need for this isn't extensive. And remember, you can work in group individually or in groups of 2. And remember, you're also going to need the modules to wire up to do this. If you didn't buy your own, you can buy them. They're inexpensive. If you go to Amazon and search for NRF24L01 module, there are options that will come up. You don't want the high-powered ones, which have an external antenna. You'll probably want the ones like were shown in the picture in the presentation here. And if you don't want to buy those, since you're only going to be using them for a couple labs, come by my office today. I'll be there from about 2 o'clock to 3 o'clock to hand those out. And you can borrow one. Now, keep in mind the ones you'd be getting are my personal ones that are from my own collection. And so stop by, pick up a couple of those. I'll have you sign it out, and then you can return them later on when we're done with these labs. Okay, so that's it for today. Work on that lab. Come by and get those parts. And other than that, everybody stay safe. I'll see you next time. If you come to my office, wear a mask. Seriously.